Hello, my name is Vincent Shemers Anakjumas, and my metric number is 05DAD5A23F1010.
My name is Jovelan Anak Rikli. My number metric is 05DAD23F1024.
My name is Mekiwanes Achanana Matthew. My number matrix is 05KD23F1014.
My name is Wilson Japang Analanta, number metric 05 DAD 23 F1016.
For Toyota Yaris GR, well, this study focus on the Toyota GR Yaris, a high-performance all-wheel drive hatchback developed with rally engineering technology. It aims to analyze how force, such as load distribution, traction, and aerodynamic effect the car motion, stability, and handling. The study connects vehicle dynamics theory with real-world performance to highlight how engineering design improves safety, comfort, and driving experience.
For discussion, during acceleration on a 4% uphill road, the rear axle carried more load due to weight transfer, while the front axle load slightly decreased. This improved traction and rear axle, especially all-wheel drive Toyota GR Yaris, giving better head grip and stability. LWD systems help maintain traction control and strong tractive force in lower gear. Aerodynamic body design reduce air drag and change fuel efficiency. The GR Yaris use stiff suspension setup for better steering handling, but not for comfort. Also, Ackerman steering geometry indicate stable cornering with minimal understeer. Overall, Toyota GR Yaris show a good balance power, handling and stability, proving its design well optimized for performance and control.
For the adjective, the first one is to analyze the understand the vehicle dynamic for the Toyota GR Yaris under different driving conditions. The second one is to study how load distribution and tractive force affect the car's stability, handling, and overall performance. Third, to evaluate the influence of factors such as weight, suspension, and tire on driving behavior. And the last one, to recommend improvement in traction control, suspension tuning, and aerodynamic to exchange stability, comfort, and safety.
Okay, for the first question is figure out the load distribution on the axle when the vehicle accelerate from a standing startup at 4% uphill road at 3.7 meter per second square, assuming the CG head is 0.5 meter. Okay. For the calculation, change the weight from kg to newton by multiply it with g, that is 9.81. Okay. For the front axle ratio and also rear axle ratio, it is 59% to 41%. Okay, move on to how to get front wheel axle weight. Okay, overall 59% multiple to lam mass of the vehicle, that is 1 16,137.45 Newton, and the answer is 9521.1 Newton for the weight of front axle. For the rear axle, 41% multiplied 16,137.45 Newton, and the answer is 6,616.35 Newton. That is the weight for rear axle. Okay, move on to C and B calculation. To get C and B calculation, we need to use WFS equal W multiple C divided by L to get C value. After move the formula until it get C, then C will equal WFS multiple by L divided by W, that is 9521.1 multiple 2.56 divided 16,137.45. Then the final answer is 1.51 meter. That is the number that is getting of C. For the B, using the same formula, but change the C to B. After putting out the number, that is 6,616.35 multiplied by 2.56 divided by 16,137.45. The final answer is 1.05 meter. That is the number of B. Okay. But because the question asks the vehicle accelerate from a standing start up at 4% uphill road, this means we need to change 0.04 degree by using tan units to tan power -1, 0.04 degree, and the answer is 2.91 degree. Okay. Now we want to checking the load distribution on the vehicle by using formula WF equal W C cos theta minus hash divided G multiple acceleration minus hash sin theta and divided it by L. After putting all the number, the final answer we're getting 7,936.35 Newton.
For the load distribution on the axles, the concept is about when the vehicle accelerates uphill, the load shifts from front to rear due to the inertia and slope. And the analysis is about the rear axle load increase to improvising traction, but the front axle load decrease slightly because the reducing steering response on an uphill. The gravitational component adds to rear axle load. It also causes during uphill acceleration more weight shift to rear wheels, which helps traction but may cause understeer.
Okay, for the next question is determine the vehicle Question A, first until fourth gear tractive force. Okay, now we start from calculation first. First of all, uh, we use this formula to get first until fourth gear tractive force. And now the question from the brochure, it uh, already provide TE number that is 400. So we put it inside the formula. And yes, for first gear, we put number 400 multiplied 3.538 multiply 3.9, then multiply 0.9, and all of that divided by 0.317. The final result for first gear is 15,669.88 Newton. For the second gear, still the same, using the same formula, and the final result is 9,912.50 Newton. For the third gear, the final result is 6,798.55 Newton. And the last gear, that is fourth gear, the final result is 5,146.52 Newton. Okay, for the analysis from first until fourth gear tractive force, in first gear, give the highest tractive force or torque first strong acceleration, but as gear increase to fourth gear, the tractive force or torque decreases due to lower gear ratios. The conclusion is while changing to first gear give torque cause strong acceleration, but while changing to fourth gear give horsepower cause high velocity. Okay, for the next question B, the threshold limit acceleration if the coefficient of fraction is 0.62. Okay, now we're going to the calculation first. For WF is 9,521.1 Newton. The CG are 0.5 meter and L are 2.56 meter. Now we're gonna using Fx max formula, that is 0.62 multiple 9,521.1 divided 1 plus in bracket 0.52 multiply 0.62 divided 2.56, and the final answer is 5,242.81 Newton. Okay, to get the acceleration, we're gonna using Fx max equal m multiple acceleration. So we need to move the Fx max until it divided by m. So we're gonna calculate or find the answer for acceleration, that is Ax. Okay, Ax multiple Ax equal 5,242.81 divided by 1,645. So the final answer is 3.19 meter per second square. For the analysis, if the coefficient of fraction is 0.62 with total acceleration of 3.19 meter per second square, then traction limiter acceleration will be 5,242.81 Newton. In conclusion, vehicle acceleration is within tire traction limits, will be no wheel slip occurs. Since 3.7 less than 6.08 average red tire, no slip occurs. The tires are well within the friction limits. That means the wheel have enough grip, so no clipping occurs.
Well, there is a modification reduce aerodynamic drag and increase fuel economy, such like front bumper spoilers. Aerodynamic surface extending downward from the bumper to block and redirect the shear flow that impacts on the underbody components. It will contribute drag and it also significantly reduce underbody drag. Low air drag, which means increased vehicle fuel economy. Second one is deck lid spoilers. Deflecting the air upwards, the pressure increase on the rear deck, creating a downforce at the most advantageous point on the vehicle to reduce rear lift. The deck lid spoiler helps reduce rear lift. It also avoids oversteer and helps tire wear out slower and reduce fuel consumption while the vehicle accelerates.
For this task, we are required to use the tire data calculator from the BND tech source website to determine the tire stiffness. Then we calculate the suspension stiffness (KS) using the formula K equal 4 pi square m. After that, we analyze the vehicle to find two main parameters: A. The front and rear axle ride rates, and B. The front and rear axles natural frequency in Hertz. First, we calculate the front and rear axle rates. The total weight for the vehicle is 1945 kg, and the tire stiffness KT obtained from the website is 270,605.535 Newton per meter. The front axle support 59% of the total weight, which equal 970.55 kg, while the rear axle support 41%, which equal 674.45 kg. Using the formula K equal 4 pi square m, we found the suspension stiffness from the front axle to be 38,350.77x Newton per meter, and for the rear axle 26,626.219 Newton per meter. Next, we calculate the ride rate using the formula RR equal Ks times Kt over Ks plus Kt. For the result, the ride rate for the front axle is 33,609.146 Newton per meter, and for the rear axle it is 24,264.85x. Next, we determine the natural frequency for both front and rear axle. For the formula used is Fn equal 0.159 square root RR over mass, and the result for the front axle is 0.94 Hz and the rear axle is 0.95 Hz. Therefore, the natural frequency for the front axle is 0.94 Hz and the real axle is 0.95 axle. This value indicate that the transmission system provided good condition and stability for the vehicle.
For my part, I will present about the Ackermann geometry illustration for question 5. So, the illustration of Ackermann steering geometry. This principle is fundamental to how cars and trucks turn smoothly without damaging their tires. When a vehicle turns a corner, it's actually tracing out a section of a circle. The challenge is that the inner wheel and the outer wheel travel along circles of different size. The goal of perfect steering is simple. Every single wheel on the car, front and back, must pivot around a single common point. We call this the instantaneous center of rotation, or simply point O. If all four axles extended out meet at this single point O, the car is turning perfectly and no tire is grabbing or sliding sideways. Besides that, if we turn both front wheels at the same angle, like a wagon car, they will not both point directly at O and the tire will slide. This is where the magic of Ackermann geometry comes in. To ensure both wheels point at the common center O, we must steer them at different angles. The inner wheel, closer to the turn, use the larger angle, which we call delta I. It has to turn sharper. The outer wheel, further from the turn, use the smaller angle, delta O. So, the difference between these two angles ensure the lines extending from both front wheel axle and both rear wheel axle all perfectly intersect at point O. For the two main dimensions, define the geometry for any vehicle. That is, I is known as wheelbase, the distance between the front and rear axle. This forms the base of the triangle that connects to point O. Next, R or Ri, which is turning radius, the distance from the instantaneous center O to the center of the wheel track. This is the size of the circle that the vehicle is tracing. In summary, Ackermann steering makes the inner wheel turn sharper than the outer wheel, guaranteeing that the entire vehicle pivots cleanly around a single point, resulting in a smooth, efficient, and wheel-reducing turns. Next is the diagram provide the geometry basics on vehicle handling and stability. As we all know that, at the very low speed, the Ackermann geometry shown is ideal. For the high speed cornering, the tire slip angle and roll become a dominant. At understeer and oversteer, it will move due to the tire force determined by its handling characteristic. For question 6, that is the advantages of tire changes based on tire specification. First of all, it will improve grip and handling, especially during cornering and high-speed driving. It will also better braking performance. Besides that, It will enhance steering response, which is low profile, known as 40 aspect ratio, which will give quicker and more precise steering feedback. It will also have a high speed stability because of ZR rating and force wheels are designed for it. Last but not least, it is lightweight wheels because BBS forced aluminum reduce unsprung weight, improving acceleration, braking and suspension performance. Next is the disadvantages of tire change based on tire specification. To start with, the disadvantage is it will reduce ride comfort as low profile tire absorb less impact, which causes stiffer ride on rough roads. Next, it will have a higher cost as Michelin PS4S and BBS wheel are premium products. It will also increase the road noise as the performance tire often generate more road noise compared to the standard one. Also, the tire will have a shorter tire lifespan as the softer rubber compounds improve grip but wear out too fast. Last but not least, it has a higher risk of damage as a low profile tire offers less protection against potholes. In conclusion, the Toyota GR Yaris demonstrates Toyota's ability to combine racing technology with modern road engineering. With its powerful engine, all-wheel drive, which is AWD system, and aerodynamic design, the GR Yaris delivers outstanding performance and precise handling. It is not just a sport car, but a symbol of Toyota's innovation in creating a vehicle that provide a dynamics, balance, and thrilling driving experience in all road conditions.
For the references, first is www.researchgate.net. For the second one is Thomas D. Gillespie, Fundamentals of Vehicle Dynamics, that are provided in CDOS. For the third one is https bndtechsource.wixsite.com home tire data calculator to use in question 4 to get the number of tire data. For the fourth one is https www.toyota.com model brochure GR Yaris brochure to get the number for all data such as wheelbase, weight, and rim size. That's all from us. Thank you.